In this video, we are going to talk about MOSFET switching, particularly focusing on Miller Plateau. Why it occurs, what are the different factors that affect it, and how it impacts things like MOSFET switching losses. Welcome to Two-Phase One Core. In this channel, we explore electronic concepts through simulations converted to cool animations like this one. For this video, we have 4 parts. We begin with the base circuit that we are going to use in this video throughout. Then in the part 2, we look at the MOSFET equivalent model that we are going to use. In the third part is where we really deep dive on the circuit to understand why exactly the plateau occurs. This is where we'll have a bit of a eureka moment, an amazing fact about the plateau that you may not have known before. And in the last and the fourth part, we look at the impact of the plateau on the switching losses and different factors that affect it. Don't worry, you don't have to take any notes throughout the video. I'm going to share this cool poster with you later on through a link in the description. For now, let's hit that full screen button and let's dive in. As you may already know, MOSFET is a 3-terminal semiconductor device which is used as a switch in power converter circuits like this one. The 3 terminals being the gate, drain, and source. The voltage from gate to source VGS is what controls the switch state between drain and source. So the circuit we are considering in this video is a simple boost converter kind of setup. On the input side, you have a current source of 100 amps. On the output side, you have a voltage source of 400 volts. When the MOSFET is on, it carries the entire input current of 100 amps and the voltage across it is 0 volts because it's essentially like a closed switch. This diode is reverse bias and does not carry any current. When the MOSFET turns off, at that time it develops this entire 400 volts across itself, turning this diode forward bias, and hence the input current of 100 amps flows directly to the output voltage supply of 400 volts. In a typical power converter like this one, the MOSFET is switching probably 100,000 times a second. It switches quite a bit. Now, in this particular simulation here, the MOSFET I have put is an ideal MOSFET. By that, what I mean is, if you look at the voltage across the MOSFET, EDS, and the current through the MOSFET, that's IDS, these two waveforms here, as the MOSFET is switching, the transitions of currents and voltages are pretty instantaneous. There's no overlap between them. So if the MOSFET is carrying a current of 100 amps, its voltage is 0. When it's not carrying any current, that's when the voltage across it is maxed out to 400. Now if you calculate the loss, which essentially is I into V across the MOSFET, you get a flat line of 0 watts. That's because there's no overlap even during switching. Even the gate voltage waveform VGS, which is shown here, is a pretty ideal waveform. All transitions are instantaneous. But in real life, the MOSFET is not like this. It's in a practical scenario, MOSFET takes time to turn on and takes time to turn off. Alright, in this simulation, I have replaced the MOSFET with a practical MOSFET model. And immediately you can see the waveforms have changed. The transitions are no longer instantaneous. Look at the gate voltage waveform. It has got that weird plateau which we want to investigate. Look at the voltage across the MOSFET. It's not going down and going up instantaneously. There's a ramp to it. And because of this kind of ramp, there's an overlap now between the voltage and current during the switching events, turning on and turning off. So both the voltages and currents are non-zero at the same time. That's the overlap we are talking about. And that overlap creates the loss. Exactly during those switching times, you have that loss in the MOSFET. This loss is called as a switching loss. And for power electronics engineer, it's a big headache. So in this series of videos, we are going to deep dive into switching losses, understand the mechanism behind it for various circuits, and try to find out some mitigation measures that are usually deployed to reduce this switching loss. But for this particular video, we are going to focus only on the MOSFET plateau, Miller Plateau, that it gets in its gate voltage waveform. It's pretty unnatural, isn't it? I mean, during this time, entire time, The gate driver has applied 20 volts to the MOSFET, and instead of rising suddenly for some duration of time, the VGS has chosen to stay flat. That's the plateau. Why it occurs can be treated like a mysterious characteristics of a mysterious device, that's MOSFET. But in this video, what we are going to do is we are going to break down MOSFET into simple resistance capacitor based model so that we can explain this phenomenon of plateau using nothing but simple basic circuit theory. So here I'm showing the most simple model of the MOSFET, the variable resistance model. Essentially, it's a switch, right? So the idea is that when the VGS is quite low, lower than some threshold of 2 volts, the MOSFET offers a high resistance, which is around what I've taken here is 1 mega ohms for this simulation. And above a threshold of 2 volts, the resistance offered by the MOSFET drops all the way down to 0 ohms, around this threshold voltage. So you can see that above 2 volts or so, the MOSFET is like a switch on, and below 2 volts or so, it's like a switch off. Simple. But in reality, MOSFET is a little bit more than this. When the MOSFET is fabricated, across the 3 terminals of the MOSFETs, you have some parasitic capacitances that are formed. We are going to name them CGS, CGD, CDS. And you also get some parasitic inductances because these things have leads, right? So every lead, every wire has some inductance. So LD, LS, and LG. And all of these parasitic elements affect the switching performance of the MOSFET. But if you throw all of this at once in a simulation, we'll never be able to find out why and what causes the Miller Plateau. So the way we are going to approach this is we are going to start with the most basic model and then slowly add these elements one by one, slowly increase complexity until we hit the plateau, and then deep dive into that circuit to understand why the plateau is occurring. Okay, so let's put this most simple model in the boost converter circuit we had and let's see what we get. Alright, now here, as you can see, I have replaced our MOSFET with the simple resistance model. There are no parasitic caps here yet, but as you can see, all the transitions of voltages and currents of the MOSFET are still pretty ideal. There's no loss here. It's like an instantaneous transition. Even the VGS waveform is pretty instantaneously changing. And that makes sense. There are no parasitics here. It's just a resistance which is changing. So it's pretty ideal waveforms. Now let's add CGS. Alright, now in this case, I have added the MOSFET CGS of around 20 nanofarads, a typical value. As you can see here, that's my gate. This is drain and source. I have kept that variable resistance between drain and source. And now what you see is that, okay, gate waveform has changed a bit. It has become like that RC charging and discharging waveform. And that makes sense. I mean, look at the circuit here. You have gate driver and basically an RC charge, right? Basically an RC circuit formed by the gate resistance of 2 ohms and then CGS of 20 nanofarads. So it's like charging and discharging, but there's still no plateau. And by the way, look at the voltage and the current waveforms across the MOSFET. They are pretty much still ideal. So it has, whatever we did, whatever we have done has not affected the power side of things. And it makes sense. I mean, look at this circuit here. On the left side, you have the control, which is controlling the switch state. On the right side, you have the power stage. And they are pretty much disconnected from each other, isn't it? This electrical circuit is not really connected. There's only one single wire here, but there's no return path. So I don't expect this to have any impact on the power side. That's why you see all the instantaneous transitions still. So CGS doesn't quite do it. Now let's add the next CGD. Bingo. Now that I have added CGD, I immediately see that plateau that we are craving for. This is my MOSFET model here now. I have gate, drain, and source. I've added a CGD of around 0.5 nanofarads, a typical value again. And now we can see the plateau occurring here. We also see some overlap between voltage and currents. The transitions are taking time now. All right, so now that we have the plateau with this simple circuit which has simple resistance capacitances, we can now finally understand why and what causes this plateau, right? So let's dive in. Let's focus on the turn on. There are three things about the plateau that we are going to understand. The first thing is how it starts. The second one is how it sustains, how it remains flat. And the third thing is how it ends. So let's divide our explanation into three parts. Through stitching all three together, we'll be able to understand why and how this plateau is formed. So let's get into how it starts. Before the plateau region, which is what is highlighted here, the gate voltage is continuously rising. The channel resistance is falling from that 1 mega ohm really high value, aiming to go towards 0 ohms. It's not quite there yet. Now, before the plateau, the MOSFET is off, the entire current is carried by the diode. This is happening because the MOSFET resistance, although it is dropping here, it's still quite high. It's so high that 100 amps, the input current, if it flows through the MOSFET, that into the resistance it is offering at the moment, something like 10 ohms or 8 ohms, that's going to be higher than the 400 volts, making this diode forward bias and eventually routing all the current to the output voltage supply. So that's why the MOSFET is not carrying any current. The diode is going to conduct until the moment this product here, 100 amps, into the resistance of the MOSFET becomes just less than 400 volts, enough to turn the diode off. And that point is simple. R is equal to 400 by 100. That's around 4 ohms. So you see here, exactly at around 4 ohms is when the MOSFET also starts conducting the current. This is the I MOSFET. Exactly when it starts offering a resistance a little lower than 4 ohms, the current, now 100 amps, starts to flow through the MOSFET and the diode becomes reverse bias. That's how the plateau region is just about to begin. That's where the MOSFET is now conducting. And as soon as the MOSFET starts conducting, the plateau region has started, right? So that's the starting point of the plateau region. We still don't know why the plateau is occurring. Let's get to that, but this is the starting moment, right when MOSFET channel starts conducting the input source current. So to understand why the plateau occurs, there's one easy way. Let's make an assumption that the VGS kept increasing instead. Let's say that there's no plateau. What would happen? At this moment, look at this, the gate voltage, I've just allowed it to increase. What would happen theoretically? If this happens, look at the resistance waveform. Now, we know from the MOSFET characteristics, if the VGS increases, the resistance falls. Simple. So, if the VGS kept increasing, look at this resistance waveform. It would have kept dropping, and would have dropped all the way down to 0 ohms in no time, right? The resistance of the channel would have dropped to 0 ohms. And this resistance we are talking about, this guy here, would have been 0 ohms. Now, just leading up to this moment, the MOSFET was off. Remember, MOSFET was off, the diode was conducting. And when the MOSFET was off, the voltage across the MOSFET was 400 volts. So these gaps, CGD and CGS, combination of them were charged to 400 volts. Look at this voltage across the MOSFET here. It was charged to 400 volts just before the MOSFET plateau began. Now 400 volts of CGD and CGS charged together, they are seeing a short circuit of 0 ohms across themselves. What would happen? They would instantaneously discharge into them because it's like a perfect short circuit. And if they discharge into it, what will happen to voltage across the CGS, which is essentially VGS? It will fall. So this contradicts our assumption where we said initially let the VGS rise. But if we allow the VGS to rise, the resistance will immediately fall to 0. And if it immediately falls to 0, there's a short circuit across the CGD and CGS, which are charged to 400 volts because the switch was off before. And now they are going to discharge into the channel. And the VGS is then going to fall because of that short circuit current. So if VGS tries to increase, it's going to kill itself immediately, because it's going to see a short circuit, and that short circuit is going to drain it immediately. So there's no way you can charge the VGS. As soon as you charge the VGS, that will get discharged through that channel because it will create a short circuit. That's how the plateau starts. Now let's try to understand how the plateau sustains this region here. We know now that VGS cannot increase. If it increases, it will kill itself by creating a short circuit, right? It has to remain flat. But how is it sustaining for that long? And what besides the duration of the plateau? That's what we are going to understand in this second part of understanding plateau, how it sustains. Now, during this region, the current through the gate drive resistance, which is around 20 volts, 2 volts is our threshold, divided, that's where the plateau is starting, divided by 2 ohms, which is around 9 amps of current. Now this current has to go somewhere, right? It cannot go inside CGS because it will just increase VGS and again end up creating a short circuit and discharging both the capacitances, and that's not possible. So that 9 amps of current has to flow somewhere. And this animation is actually showing nicely where it's going. During the plateau, this 9 amps is fully flowing through the CGD. It cannot flow through CGS because of the reasons we just said. And all of these 9 amps, look at the direction of the current here. It's like a constant current of 9 amps because 20 is fixed, 2 volt is fixed because of the plateau. So it's a constant 9 amps of current continuously discharging your CGD. So during this plateau region, your CGD is continuously discharging. That's why you get a ramp in voltage across the MOSFET, because voltage across the MOSFET is nothing but the voltage across CGD plus CGS, right? This is what is showing that CGD capacitor discharging, and it's discharging linearly because if you discharge a capacitor with a constant current, it drops like this linearly. So this is what is happening when the plateau is ongoing. The CGD is getting discharged with that 9 amps of current. Now let's focus on something more interesting here. Right in the middle of the plateau, let's take that point, right? The voltage across the MOSFET has fallen down to 200 volts. It's carrying the full current of 100 amps. So looking at the MOSFET here, the voltage is 200 volts. It's carrying a current of 100 amps. If you just purely look at the resistance of the MOSFET, which is nothing but V divided by I, which is 200 by 100, it should be around 2 ohms, which is what we see here on the resistance waveform as well. So this is a little more interesting, isn't it? I mean, we started the plateau with the resistance of 4 ohms, and now we have dropped to 2 ohms. What's happening here? We thought during the plateau, only CGD is discharging. But there's something more at play here. The MOSFET is effectively turning on slowly. Look at this resistance waveform of the MOSFET. It's dropping slowly. It's turning on slowly during the plateau region. I think it makes sense. I mean, during the plateau, the voltage is continuously dropping. Current is the same. So, of course, the resistance has to drop. The MOSFET is slowly turning on as the CGD is discharging during this plateau region. And you know what is more staggering? If the resistance of the MOSFET is falling, how come VGS is constant? I mean, VGS, we said right from the beginning, is the control handle on this switch. And I am holding the control handle because of the plateau, it's being held at a constant voltage of 2 volts. And now how can you tell me that resistance is dropping and the MOSFET is turning on even when VGS is constant? This doesn't make sense. There has to be one-to-one correspondence. If resistance is falling down, slowly, the VGS also needs to increase. How can it be constant, right? Doesn't make sense. So let's zoom in on y-axis of this waveform to confirm. Bingo. There you have it. Now I have zoomed in a lot on the VGS waveform. And what you see is, as the resistance of the MOSFET is falling slowly, the VGS is also equally slowly increasing. It's really, really slow increase. That's why we couldn't see it on the scale. The plateau almost appears like a flat waveform, but it can never be flat. That's the eureka moment of this video. The plateau, no matter what you see in the textbooks, can never be flat, because during the plateau region, the CGD is constantly discharging and the voltage across the MOSFET is constantly falling. The current through the MOSFET is constant. So if the voltage is falling, current is fixed, then the resistance has to fall slowly. So if resistance has to fall slowly, VGS has to increase slowly as well. It cannot be flat. That's the important thing. So any MOSFET waveforms you see, and you see a flat plateau illustrated in the textbook or somewhere else, just know that it will never be flat. You just have to zoom in enough and the plateau can never be flat. That's the amazing thing about it. Okay, now that we have seen how the plateau sustains and what happens during this amazing plateau region, let's see how it ends. The culprit behind all of this, the plateau itself, has been the CGD, right? And when the CGD fully discharges to zero, then there's nothing for VGS to be afraid of. It can rise freely. Why? Because, well, CGD is fully discharged. So it's okay if you create a short circuit for it, because there's no voltage left in it. What will cause the short circuit? There's no short circuit current that will flow. So that's when the plateau ends and VGS can finally freely increase. So there you go. This was the part 1 of the video where we explained why the plateau occurs, right? Now on to the next part where we see how it impacts things like switching losses and what are the factors that affect the plateau. Now here for the exact same simulation, I'm just showing the MOSFET loss waveform as well. As you can see, exactly during the plateau region, we have MOSFET switching loss. And this makes perfect sense for our circuit. Like we just discussed, during the plateau region is when the voltage across the MOSFET is falling. And exactly during this time is what the overlap is between the current and the voltage, leading to the loss. So this triangle that you see here, area under this triangle, is the switching loss energy that gets spent when the MOSFET turns on. And it's clearly, that time is clearly dictated by how long your plateau is sustaining. So the duration of the plateau is determined, as we discussed already, based on how long CGD takes to discharge. So this is just CGD discharging. As soon as it goes to 0 volts, the plateau will end. So is there a way we can discharge this CGD faster? So if you remember, the current that's discharging the CGD, the current that flows through this gate resistance is 20 volts minus 2 volt divided by 2 ohms, which is around 9 amps of current, constant current discharging this CGD. So how can we discharge it faster? The first thing that comes to mind is just replace this 2 ohms with maybe 1 ohm gate resistor and get 18 amps of discharge current. So it's basically double the current. Use that double current to discharge the CGD faster. Let's see if that works. Let's rerun the simulation with 1 ohm of MOSFET gate resistance. Alright, that worked. So I have reduced this gate resistor to 1 ohms. Now the CGD current is 18 amps twice, and that is discharging my CGD much faster. So I'm kind of plotting both the waveforms together. There is a faint waveform, which is the previous loss waveform with the 2 ohms, and the brighter waveform is the one with the newer value of 1 ohm gate resistor. As you can clearly see, the MOSFET loss triangle has reduced in size. So clearly my MOSFET switching loss has reduced. The plateau has reduced too, as expected, and the VGS, the voltage of the MOSFET is falling quicker too. So this is how important that gate resistor is. It's another control handle you have, a control handle to tell how fast I want to turn on my MOSFET. The faster you do, the lesser is the loss, the lesser is the plateau. That's how it works. Now, what else do you think can affect the plateau? What about CGD itself? If I got a really bad MOSFET from the market that has really bad value of CGD, here I am using 0.5 nanofarad. What if I have a MOSFET which has a CGD of 1 nanofarad, twice the value? What do you think will happen? So in this simulation, I have just changed that CGD value to 1 nanofarad. And as you can see, because now that same 9 amps of current which is discharging it, the current discharging the capacitor is the same, but the capacitor value itself has doubled. So it's going to take twice the time to discharge. So instead of discharging in this time, now it is taking a long time for discharging fully. So the plateau has almost doubled in size, and the switching loss triangle also has doubled. So it's almost twice the loss, more loss. So it's very important to look at this parameter CGD when you select the MOSFET. It essentially determines how good your MOSFET is going to be in terms of losses. Alright, so that was about the losses and what are the factors that impact the plateau. What about the turn-off plateau, which is the plateau you get when the MOSFET is turning off? We only talked about turn-on plateau in this video. Do you think the same explanation applies for the turn-off plateau as well? Let's keep that for some another time. Let me know your thoughts in the comments. This one more thing, by the way. We only assumed MOSFET to have these two parasitic capacitances, CGD and CGS, in this video, and that was enough for explaining the plateau. But what happens if you add the other capacitance, CDS, other parasitics such as the lead inductances, LD, LS and LG? How do they impact the switching behavior and switching losses? So there's a lot of questions still to be answered, and we are going to tackle all of them in the upcoming videos. So if you found this video useful, please subscribe to Two Phase One Core and stay tuned